Good morning, dear student. Let us start module 4, which talks about stability analysis and frequency domain analysis and stability. Okay. The first part of the module 4, we will be talking about the stability analysis. That is, Routh-Hurwitz criteria we will be using, and we will be analyzing the stability of the system. The entire module content will go like this. Concept of stability, necessary condition for stability, root stability criterion, relative stability analysis. We'll be dealing more on root stability criterion. Next concept what we have to discuss is introduction to root locus techniques, the root locus concept, construction of root locus. Next part is frequency domain analysis and stability. That is stability analysis in frequency domain we will be discussing. That is correlation between time and frequency response, Bode plots, and we will be having experimental determination of transfer function. This is about the different concepts we will be going through in module 4. Definition of stability. So we define stability in so many ways. Okay, a system is stable if its output is bounded for any bounded input. Okay, for the bounded input, if bounded output available, then we call that system as stable. And we also define asymptotic stability. A system is asymptotically stable if in the absence of input, the output tends towards zero or the equilibrium state irrespective of initial conditions. This is the other definition we can give. We call this as asymptotically stable conditions. Okay, and we also define a system as stable for a bounded disturbing input signal. The output vanishes ultimately as it approaches infinity. So this is also another definition. Here we say that if the input is a disturbing input, then it has to dies out as t tends to infinity for system to be stable. So that's what the third definition we say. And the fourth way of defining same stability, a system is unstable if for a bounded disturbing input signal, the output is of infinite amplitude or oscillator. Okay, so this definition says that if the input is bounded and the output is reaching infinite or if it is oscillating, then we call such system as unstable system. Okay, so this is also the way of defining the stability of the system. So another definition what we have, the fifth one here mentioned, that is for a bounded input signal, if the output has constant amplitude, then the system may be stable or unstable under some limited constraint. Such a system is called limitedly stable. Okay, so we found a few systems stable for only selected conditions, not for all the conditions. Okay, that is what we call it as constrained stability or constrained stability of the system. Only for few conditions it is stable, and for rest all the condition it will be unstable. So we call that as constrained, stable systems. And we have, in a system, output is stable for all the variations of its parameter, then the system is called absolutely stable system. So this is what we call it as absolute stability. This is what we are looking for. So we want a system to be stable for all the variation of its input parameters. Okay, this is what we call it as absolute stable system. This is what we will be looking for in any control system. Okay, so here in this slide we have discussed the different way of defining stability. So in different literature you will find different definition for stability of a system. So next in this chapter we have this concept, that is Routh-Hurwitz stability criterion. So Routh-Hurwitz has defined one stability criterion. We apply that and we will declare the system as stable or not. Okay, so this method is applicable to continuous system stability estimation. Okay, only for the continuous system stability estimation we can use this. Okay, this system, that is Routh-Hurwitz criterion, this always gives the number of characteristic equation roots, that is roots of the characteristic equation, which are in the right side of the S plane. I repeat, this Ruth-Hurwitz criterion gives us the number of roots to the right half of the S plane which is causing instability as the number of sign change in the first column of the Ruth table. Okay, so we will be writing a Ruth table here according to the Ruth-Hurwitz method or Ruth-Hurwitz stability criterion. We have to construct a table. In that table, the first column, the number of sign change will gives us the information about the number of roots to the right half of the S plane, which causes the instability. Okay, so thus it is going to give us the information about the stability of the system. Okay, so here the stability of the system, we will get to know without solving the closed loop system poles. Okay, we don't do much analytics about the characteristic equation. We simply plot, we simply write the Ruth-Hurwitz table we will write, and in the table we will observe the first column which gives the information about the number of roots which can lie in the right half of the S plane. Okay, so as we have seen in the last slide, it is going to give us the number of roots which can occur in the right side of the S plane as as equal to the number of sign changes in the first column of the root table. Remember here, it is going to give us only how many roots are there to the right half of the S plane. It will not give the exact locations of those roots. Roots location which is causing instability, we will not get to know. We will get to know only how many roots are there to the right of the S plane which is causing the instability. Okay, this method requires only two things. We have to generate the table first. Okay, to looking into the characteristic equation, we have to generate the Ruth-Hurwitz table and we have to interpret the table properly. Okay, so the first column we have to observe, the first column, while observing the number of sign changes which is occurring, will gives us the information about roots which are lying to the right of the S plane. Based on that, we comment on the stability of the system, which is going to tell us, the root table is going to tell us how many to the right side of the S plane, how many roots to the left of the S plane, and it also tells us how many roots on the imaginary axis. Okay, this all, after writing the root table, we will analyze the root table, we interpret the Ruth-Hurwitz table to get to know these information. Okay, here is how we are constructing the Ruth-Hurwitz table. Okay, so first we have to take the characteristic equation. So here we have taken in general nth order continuous system. Okay, nth order continuous system characteristic equation we have taken, that is an s power n plus an minus 1 s power n minus 1 plus so on till a1s plus a not equals 0. Here we have taken the characteristic equation of nth order. So we will see how Ruth-Hurwitz table has to be constructed. How to construct the Ruth-Hurwitz table. The first two rows of the table, we have to write it just looking into the characteristic equation. Okay, so first row I call it as s power nth row of the Ruth-Hurwitz table. So I'll be taking s power n coefficient. I'll skip the next one and I'll be picking up the next one. So like that, I'll be picking up the alternate, coefficient in the first row. And in the second row, s power n minus 1, whatever the coefficient left out, I'll be taking. Okay. So the first two rows of the Ruth-Hurwitz table, we will fill up by looking into the characteristic equation. Okay. Third row onwards, we will be computing. We will be computing these, table entries, how we can compute. So here we have written what is B1, that is third row, first element. What is B1? B1 is equal to this coefficient an minus 1 into an minus 2 minus an into an minus 3 divided by an minus 1. That is what b1. What is b2? B2 is you have to take the first column and you have to take the third column. Okay, you have to consider first and third column. So that is an minus 1 into an minus 4 minus an into an minus 5. So you have to take secondary diagonal element minus the primary diagonal element divided by the base element, that is an minus 1. We call this as a base element and we have to take the base element. So now what is B3? B3 is again you have to take the first column and you have to take the third, fourth column here. So fourth column we have not entered here. So for the sake of simplicity, you can have terms and you can write the equation for B3 also. You have to extend the same logic and you have to compute. Similarly C. So for computing C1, that is the fourth row here, we have to take the an minus 1 and b1, these two elements in the column 1 and an minus 3 b2 in the column 2. So you have to take these four elements, and in these four elements you have to take secondary diagonal elements product minus primary diagonal element product divided by the base element, we call it as. Similarly, C2, how to compute? You have to take an minus 1 and b1, these two elements of column 1 and these two elements of column 3. We have to take it. So we have to go secondary diagonal element b1 into an minus 5 minus an minus 1 into b3. That is principal diagonal element. Difference you have to take divided by the base element b1. So on. So here we have a particular example with s power 4. Okay, with the highest degree here is 4. So this is fourth order characteristic equation we have. So how to fill up the Rutherford table? So fourth order equation we have. So we'll start with s power 4. That is the first row element is s power 4. So here what we have is the fourth order characteristic equation we have. So first row is what the fourth order coefficient we have to take it. So first element is a4. I should skip s power 3. I should take up s power 2, that a2 coefficient I have to take, and s power 1 I'll skip and a0 I'll be taking here. So s cube is the next row element. So I'll be taking s cube coefficient, which is a3, and I'll skip s square coefficient. I'll be taking s coefficient and the constant, whatever it is. Okay, so this is how not the constant, we don't have any term here after that. So whatever we'll be taking in the first row, the alternate missed coefficient will be taking here in a sequence. So this is how we will be filling the first and second row of the Rutherford table. So third row onwards we have to compute. Okay, so what is the third row first element? So I have to take here first two column element I have to take it. So I have to compute the determinant of this. So it is minus of this determinant divided by the base element a3 is what b1. Similarly, what is b2? B2 is you have to take this column and you have to take this column as a matrix. You have to compute the determinant, you have to attach minus and divided by the base element a3. That is what b2. Similarly, what is b3? You have to take first column, you have to take here the fourth column, which we don't have. Okay, that's why we are getting here a value 0 divided by the same base element a3. Okay, similarly for s power 1 row, this is s power 1 row, we call it as. We will repeat the same procedure, but now determinant consideration we will be doing like this. So a3 and b1, a1 and b2 is the matrix we will be considering. We'll compute the determinant divided by the base element b1, and this is minus according to definition, which is actually c1. Similarly, to compute C2. To compute C2, I have to take this column and the last column. So you could see here in the last column we have 0, 0. In the first column we have A3 and B1. So computing the determinant, you will find 0. So we'll be having here entry 0, here also obviously 0. So finally S power 0th row we have to fill up in the Rutherford's table. So here again the same convention, that is you have to consider B1 C1 and B2 C2 actually, which is 0. So you have to take this determinant multiplied by minus divided by the base element C1, which is equal to D1. Similarly, this D2 term, similarly, this D3 term we have to compute, but it leads to 0. It leads to 0 because you can see here the determinant element one column, it is 0. Determinant value will be 0. So finally the component will become 0. So this is how we will fill up the Routh-Hurwitz table. Okay, so number of rows of a Routh-Hurwitz table depends on the order of the characteristic equation. Higher the order, you will find higher number of rows in the Routh-Hurwitz table. Okay, so next is we have okay. Next we have the different cases which we encounter while filling the Routh-Hurwitz table. So while filling the Routh-Hurwitz table, it will not be always the same situation. We will find different situations here. So as the situation changes, we will change the procedure to fill up the table. Okay. So finally, objective is to fill up the Routh-Hurwitz table. Once the Routh-Hurwitz table finished, then only we can comment on the stability, otherwise no. Okay, we come out with 4 standard cases here, and case 2 is having 2 different solution inside. So we say that totally we'll be having 4 methods to solve the different situation which we can encounter in a Routh-Hurwitz table. So case 1 is one where a situation will arise, that is in the first is that is the first column you will not find 0. You will not find any element 0 in the first column. That is a normal situation, comfortable situation to comment on the stability of the system. So that is one case. You will have everything standard. You will see that there is no zeros in the column 1. There is no difficulty in computing the table elements. You can comfortably complete the Routh-Hurwitz table and commenting on the stability. That is case 1. Case 2, what we have is a 0 in the first column we will get. Only first column element we will find 0 and the other elements will be non-zero. Okay, so this is what we call it as a difficulty. If the first element becomes a 0, then that is what is going to denominator for the next row computation. So we will see that the component value will be leading to infinity, which is not proper. So that is what we have a difficulty in completing the table. So how can we manage that difficulty? Again, we have 2 solutions to that problem. So in the case 2, we will be having 2 different scenario to be studied. So totally we have taken 4 special cases. That's why. So third case is where we will find entire row is 0. So if that situation arises, how to handle that is, we will be learning that. So totally we'll be talking about 4 different situations and 4 different solutions. So first case we will take up. So in first case, you will not have any problem here in completing the Routh-Hurwitz table. You will not encounter in the first column 0. Okay. So here is what the continuous system having characteristic equation s cube plus 6s square plus 12s plus 8 equals 0. Okay, how to complete the Routh-Hurwitz table here? So s cube, how I have taken the coefficient, s cube coefficient is 1 that I have here. I will skip s square and I'll go to s term, which is having coefficient 12, and I should skip constant, and the next value is not there, so I have 0. Now next is s square row. I'll start from s square coefficient, which is 6. I should skip this. I have to take this constant and then no other term, that is 0. So S power 1, how we can compute? S power 1 we can compute this way. 6 into 12 minus 1 into 8 divided by 6. 6 into 12 is 64 divided by 6 is what the first term we have. Okay. Next, how to compute the second term? To compute the second term, I have to take 1 and 6, 0 and 0. So these four elements I have to consider to compute this element. How to compute 1 into 0 is 0 minus 6 into 0, 0. So I have 0. Okay. Next, how to compute this s power 0 this term? How did I get this 8? So I have to multiply 64 by 6 into 8 minus 6 into 0. Okay. So 64 divided by 6 into 8 is what we have 8. Okay. So anyway that the other term will be 0. So how we got this 8 I have explained. So now I have to observe the first column element here. Is there any sign change? No, there is no sign change in the first column entries of a Ruth Hurwitz table. So system is stable. Okay, since there is no sign change happening, all are positive, there is no sign change happening, so the system is stable. We conclude like that. Okay, so next, so we have next example here. I have taken s cube plus s square plus 2s plus 24. So this is third order characteristic equation we have taken. So let us complete the Ruth Hurwitz table. So what is the first row element? S cube I will be starting, that is highest power. S cube having coefficient 1, so I have 1 here. I have to skip s square. I have to go to s coefficient, coefficient of term s. I have two, and this I should skip. Next term is not there. Okay, so I don't have any further elements. Next is s square row. In s square row, we have to take coefficient of s square, which is 1. Coefficient of s we have to skip. Next term is 24. I have taken here. So now s power 1 I have to compute. Only first two rows of the Ruth Hurwitz table we copy from the characteristic equation. Third row onwards we have to compute. As we have seen the formulas, how to write, how to compute s power 1. S power 1 row to compute, I have to take here secondary diagonal element, that is 1 into 2, that is 2, minus 1 into 24, 1 into 24, that is 24, divided by the base element, that is 1. So we have 1 into 2 as 2 minus 1 into 24 as 24. The difference is 22. 22 divided by 1, we have minus 22 here. So how to compute this element? This element again I have to consider this first two element of this column, and here there is no element, so I have 0. So how to compute s power 0 first element? It is minus 22 into 24 minus 1 into 0 divided by 22. So if I do that, I'll be getting 24 as an answer. So I have here. Look into the first column element of the Ruth Hurwitz table. First column element, if you observe, you could see that there is two sign change. I repeat, there is two sign change. How? You can see here, the sign of this is plus, sign of this is plus, sign of this is minus, sign of this 24 is plus. So come here from the first element. Plus to plus, no sign change. Plus 2 minus, there is one sign change, and minus to plus again here happening. So minus to plus again it is another sign change. So totally I say that there is two sign change. What's the inference? In the first column of the Ruth Hurwitz table, if you find two sign change happening, twice the sign change happening, then we say that to the right half of the S plane, there exist two roots. Okay, two sign change because to the right half of the S plane, there exist two roots, so system is unstable. Okay, so next we have, next we have S cube expression, that is third order expression, and we have here a constant k. So what we have to do is we have to find the value of k for which the system is stable. Okay, I have to now calculate this unknown value k for which the system is stable. So now what we do is we try to write the root Hurwitz table. So that is, first row and second row we will fill up according to the characteristic equation. So based on the characteristic equation, I have taken s cube coefficient 1 here. I'll skip the s square term. I'll go to s term. I have taken 3. Okay. And constant, I'll skip it. Okay. So I'll go to the s power 2 row. Then I have s power 2 coefficient 3 I have taken, and 3s I cannot take it. The constant 1 plus k I have taken. The other element is not there. It is 0. Okay. So now I have to compute this element. How? It is 3 into 3, 9 minus 1 into 1 plus k. Okay. So if I compute that, I'll be finding 8 minus k in the numerator divided by the 3. What we have here, that 3 we will be taking here. Similarly, how to compute this? I have to multiply this. That is 8 minus k divided by 3. I should multiply with 1 plus k minus 3 into 0 divided by 8 minus k divided by 3. Okay, so denominator 8 minus k by 3 will get cancels with numerator 8 minus k divided by 3. I will left out with only 1 plus k here I have taken. Okay, now for system to be stable, I want there should not be any sign change in the first column. If there is no sign change happening in the first column, then this term should be greater than 0. And again, this term should be greater than 0. Okay. So we have here 8 minus k has to be greater than 0, and 1 plus k must be greater than 0. Then we will not find any sign change in the first column. Then we can declare system is stable. Okay, so we have according to these two conditions, we can say that the k must be having value, or k must lie between -1 and 8. Okay, so here we can say that 1 should be less than k and k should be less than 8. Okay, between these two things it has to oscillate. Okay, so between these parameters it has to change for system to be stable. I'll stop here. I'll continue with this in the next class. Okay. Thank you.